So this technology, we are going to this week and next week, we're going to speak about first about solar collectors for domestic hot water, and then the PV collectors, probably for the PV panels. We will be working with them for more than 1 week, but I think 1 week for this would be enough. If you're working in your capstone, I would recommend you use this, even if it's not, if your client's not demanding that, but at least you have to study. We can work with solar collectors for heating system, or the domestic hot water. At least you have to, if you are working with your capstone project here in this course, you have to calculate how many solar collectors we need for the domestic hot water. Okay. If you want to use it for the heating system, let me know, and we can. But it's not more complicated, but we have to work a little more. First, we have to understand the difference between two technologies. Okay, so we have what we need in our building, and we have the solar technologies that we have available. Basically, we only have we have solar thermal collectors, photovoltaics, and then we have the passive solar. We know what the passive solar is. It's about orientation of openings. Okay, if we have curtain walls or big openings, we have to orient. We have to place those openings in the right place, in the right facade. But these are the building needs. We have domestic hot water. We have heating, cooling, light, and electricity. So this is what a building needs: domestic hot water, heating system, a cooling system. We need light, and then we need electricity to run all the appliances. And these are the technologies that we have here. If we have the solar thermal, what can we do with solar thermal? We can work with domestic hot water and heating. You see that we have cooling here with a dashed line. In theory, we can use solar thermal collectors to heat up water, and we have an appliance to work with the cooling, with the building cooling. This is what we call solar cooling. Okay, so there's a way to do that. We can use solar collectors. With solar collectors, we can heat up water, and we are talking about solar collectors with hot water. We are not talking about PV panels. Most of the pictures that you will find online, it's about using PV panels, solar cooling. Yes, you can generate electricity, and then with that electricity, you can use that electricity with a heat pump, and this is solar cooling. Yep, but there's another thing. So we can use solar collector, we can have hot water, and then we can have this absorption chiller, and it uses the energy that we have in hot water. We turn that energy into a cooling device. It exists, and it's wonderful, because the problem that we have with the solar collectors is that we generate the maximum hot water when we don't need it. Okay, so we have hot water, a lot of hot water in summer. In summer, we do need domestic hot water for the showers, but we don't need hot water for the heating system. So it would be great having a lot of or it would be great having a device that can make the most of all this hot water that we can generate in summer, and using that energy for the cooling system. Well, that system exists. It's the solar absorption for cooling. Okay, so you will find a lot of articles, scientific articles, but you won't find a lot of examples. There are examples, and I know architects that have used these devices, and they all told me that they will never use this system again, because it's very expensive, it's very complicated, and it works, but it's too expensive. Basically, what they have to do, they have to heat up water up to almost the boiling point, and then they can use this energy. There's a device that can extract that energy, and they can turn this energy into something that cools down the building. The technology exists. 20 years ago, it seemed a good idea, but some people have used that technology in buildings, and it doesn't work. It's too complicated and too expensive, and savings in the long term are not that much. Okay, but that's why we have this dashed line here, because with solar thermal collectors, we can even use this energy for cooling a building. But it's not mainstream, and the technology has been in the market for 20, 30 years. And if something is in the market for 20 years, and if it doesn't become an option, it's because it's not a good technology. But who knows? Maybe in the near future, they will find another technology more affordable, but so far it's not. Okay, but this dashed line means that using solar collectors, we can have cooling. The only thing is that the technology, it's very complicated, it's very expensive, and nobody does it. Okay. So basically, with solar thermal collectors, we can have domestic hot water. Probably is the most efficient way to generate domestic hot water using solar thermal collectors. We can have heating. We can use or we can generate hot water for our heating system, but this heating system is limited to a hydronic system. We need hot water. So what systems do we have with what heating systems do we have using hot water? Radiators, radiant floors, and fan coils. Okay. If we want a heat pump, we can't use solar thermal collectors. If we have an electric system for heating, if the heating system uses water, we can use solar thermal collectors. And then we need cooling, lighting, and electricity. If we need either cooling, lighting, artificial lighting, or electricity, we need photovoltaic panels. Okay. So that's it. And then with passive solar, it's good. We need to take it into account, but it's not reliable. If we don't have sun, if it's a cloudy day, we don't have passive solar gains. So it's something that we have to take into account in winter. On a sunny winter day, we can make the most of the sun with passive solar strategies. But if there is no sun, we need a heating system. Okay. So a passive solar, it's a good alternative. It's like natural ventilation. It's great when the outdoor temperature is almost a comfort temperature. We can rely on natural ventilation. If the outdoor temperature is 0 Fahrenheit, there is no point in having natural ventilation. So the passive solar is the same. When we have a sunny winter day, it's great. If we don't have sun, then we can't use it. So basically, we have these two solar technologies: solar thermal collectors for domestic hot water and heating, and photovoltaics or photovoltaic panels. Solar thermal systems make sense for off-grid homes. That's true. Imagine that we are in the middle of nowhere. We don't have access to the water from the grid, or then we need to generate our own energy. So we can have PV panels if we need electricity, but if we just want hot water, the solar thermal systems, it's the best option. Okay, so if we don't have access to water, we need solar thermal systems. And then this is very important. Heating water is very expensive. Okay, so the hot water that we need for the shower, even if we have a shower, we take a shower only once or twice a day. This is around 20% of the domestic energy used of the domestic energy that we need, or of the daily energy. So we need a lot of energy to heat up water. And if we have an electric water heater, electricity is the most expensive way to heat water. Okay. So keep that in mind. Electricity, if the electricity, well, it's the most expensive way to heat water. Then we can think about, okay, so where does the electricity come from? What if I have a PV array in my roof? I generate the electricity, and then I use this electricity to heat up water. Okay, yeah, so, but it doesn't mean that it's not expensive, because you have to place a lot of PV panels on the roof. So it's expensive, okay? If we're talking about money, probably burning something, burning gas or burning fuel is the most efficient and the cheapest way to heat up water. And we do need domestic hot water, okay? So, and this is, so we have, there are a lot of things that we have to take into account. I am, it gets on my nerves now with this energy crisis that we have, especially in Europe. It gets on my nerves listening to all the experts or politicians talking about electricity or energy in Europe. There is so much bullshit that I'm angry at that. But keep that in mind. If we need hot water, what can we do? If we have a solar collector, we make the most of the sun, and we generate hot water. This is for free. Well, for free. We have to pay the price of the solar collector. Solar collectors for hot water are quite cheap, and the installation, it's not difficult. We have problems with the freezing and all that stuff, but it's quite cheap. And once we have all the installation there, the generating hot water is for free. Then we can burn a fuel. Okay, if we burn the fuel, we have an efficiency of, let's say, 80%. Okay, 80% of the energy that we generate by burning fuel, we can use this energy on heating up water. Okay, so that's why this burning fuel is very efficient. And then we have electricity. And we have electricity to heat up water. So where does this electricity come from? Okay, if we have PV panels, we can generate electricity. The efficiency of this PV panel is around 10%. Okay, so we need 8 times as many PV panels to generate the same electricity or the same amount of energy. And we need 8 times as many PV panels as solar collectors because of the efficiency. This efficiency of the solar collectors can be around 80% as well. Okay, so 80% of the sun energy we can turn it in hot water, but only 10% of the energy of the solar energy we can turn it into electricity. And then we need to use that electricity to heat up water, and it has another efficiency, probably let's say 70%. Okay, so it's a question of efficiencies that we are losing. We have the energy in the sun, that's the energy. So if we use 80% of that energy, the energy that strikes on the solar panel to generate hot water, that's it. If we use the energy, the same energy that it's hitting on the PV panels, we can use only 10% of that energy. We generate electricity, and then we lose part of this electricity in generating hot water. So that's why the system is not very efficient. And once you have the PV panels, again, it's for free. Okay, so you have the PV panels, a lot of PV panels on your roof to generate your electricity, and then you have your own hot water. But in my humble opinion, what it doesn't have any sense is if we have electricity here, and that electricity comes from the grid. What is this grid? We don't know what this grid is about. we can have renewable energies. We can have PV, or we can have wind, or geothermal. I don't know. We can have renewable energies. Nowadays, we look at the energy mix. This is less than 15% of the energy mix of different countries. It can be from 10 to 20. If we are close to 20, this is a lot. If we are close to 10, this is not as much. But only 10 to 20% of the energy comes from renewable sources. And then we have fuels, gas, oil, and other fuels. We do have biofuels. And we have nuclear. We can use as, or we can consider as renewable energy the hydroelectric. Okay, so when we get electricity from the grid, and we use this electricity for the grid to heat up water, we don't know where this energy is coming from. We can assume that, okay, let's be optimistic, 20% of this energy comes from renewable energies. Let's say 50% comes from fuel and gas. Let's say that 10% comes from biofuel, and 20% comes from the nuclear. Does it add up? Yeah, okay. It's 100, kind of. That depends on the energy mix of the country. So using this electricity from the grid to heat up water is the worst business that we can have, because especially if we are burning fuels, okay, we are burning fuels to generate electricity. So here we are losing, or we have an 80% of efficiency. We are losing 20% of the energy that we have in this fuel. Then we need to transport the electricity from the thermal plant, or from the plant, the energy plant, until our city, our house. And we lose a lot of electricity here. Let's say that 20% of electricity we have losses. Okay, so here we lose 20% of the potential. Here we lose 20% in transportation. If we have our boiler here, and we just use this boiler to generate hot water, it's much more efficient than generating electricity here and using that electricity there. So if there's a time in which this energy, this electric energy on the grid from renewable sources, it's 80% of the energy mix of the country, that's fine. But nowadays, using electricity from the grid to heat up water is the worst business we can have in terms of money and in terms of CO2 emissions, because with this we are emitting CO2, and with this, of course, we have emissions CO2. But the emissions that we need, because we are losing a lot of energy here. So this is CO2 that we expel, and we can use it because we are losing a lot of energy in this process. If we burn this fuel at home, we don't lose anything on transportation because our boiler is on the basement, and or the domestic hot water is on the bathroom or whatever. It's on the first or the second floor. So this is much more efficient than this. And probably if we take into account the CO2 emissions, this is more efficient and more environmental friendly than this, depending on the energy mix of the country. But this is the average for every country. Okay, so probably some of the countries, this is it's not 50, it's 60. This is not 20, it's 15. And this is not 10, it's 5 or 6, and this is 30. But we don't have a country nowadays that I know of There is no country that produces 80% of the energy that the country needs from renewable sources. Doesn't happen yet. Are we moving in this direction? Yes, we are moving in this direction. But nowadays, using electricity probably is the worst thing we can do. This building uses electricity. You see a lot of, I know, we are using electricity for a sustainable future, whatever. Yeah, that's fine, but we do have solar collectors. Okay, so in this building, the hot water doesn't come from the electricity, it comes from the solar collectors. So what are we doing? We are using solar collectors, at least for the domestic hot water. And in this building, we're using electricity. We have a PV array, and we have electricity for the rest of the things. It's a debate whether this building would be better if we had a hydronic system like a radiant floor, and we had more solar collectors. I think the building would be more efficient in that way than the way it is, having a huge PV array to generate electricity and use this electricity for the heating system. But we can talk about it. I can have an opinion, the other one can have another opinion. I will show the other one my numbers, the other one will show me my number, their numbers, and we will make a decision with that. But using electricity from the grid to generate domestic hot water is the worst thing we can do. Okay? So that's it. We can debate, or we can have different opinions about using electricity from our PV array. Is it better than using solar thermal collectors? It's going to be more expensive, but you can say, no, my client will be safer because that family is not exposed to freezing or whatever. Okay, so there, we can talk about it, but you have to keep in mind that so far, nowadays, I don't know in 20 years, I don't know in 50, I don't know in 100 or next century, but nowadays in 2022, electricity is the most expensive way to heat water. And now this is also interesting. If we are talking about efficiency in buildings, and now we are talking about residential buildings, we're not talking about commercial buildings, but in residential buildings, the way of living matters. If we have a single family house, this is the amount of energy that we spend on heating. If we live in a residential building, in an apartment building with different flats, different apartments, this is the amount of energy that we spend on heating. You can see the rest of the figures are the same. The appliances, the domestic hot water, the lighting, and the kitchen, it's almost the same, but the heating matters. So it's much more efficient living in buildings, in residential buildings, than living in single family houses. Okay? That's a fact, and it makes sense. Why? Because if you have a single family house, a detached single family house, the envelope, we are losing energy through the walls, the roof. If we are in an apartment building with houses like this, the area exposed to the outdoors, the thermal envelope, is just this. If we have a detached house, the exposed envelope, or the thermal envelope, is like this. Okay, so if we have the same square footage, the amount of envelope that we have in a residential building is just this. In a single family house, we have these walls and the roof. We have different floors. This flat is not even using energy through the ceiling because we have another flat above us. but this is about the way of living. Can we tell now all these single family houses that we have here? No, 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 no. You have we have to demolish all this, and then we have to build residential buildings with 4, 6 floors. I don't know, but that's if we're thinking of a new development for residential buildings or housing, moving to this option, it's more efficient from the energy point of view, because we save a lot of energy in the heating system. Okay, so this is something when we are when we are talking about energy, we have to talk about this useful energy. When we are talking especially about solar energy, we have absorbed solar energy minus the thermal losses. Okay, so this is the efficiency. This is what we call useful energy or efficiency. We have the total amount of energy that we have in the sun, and then we have a system, and that system has different thermal losses to turn this energy, this solar energy, into either hot water or electricity. If we have a PV panel, the useful energy that we get out of the solar energy is very low. We are talking about 10%. If we have domestic hot water, the useful energy is around 80%. Okay, so if we have the same amount of solar radiation with a PV panel, we can generate only 10% of electricity. With a solar thermal collector, we can generate 80% of hot water. Okay, but it's energy. And this is when we are assessing the performance of solar thermal collectors, we need this solar fraction, this F. Okay, so the name F chart comes from this solar fraction, which is the energy, is the relationship or the ratio between the solar energy divided by the total load. Okay, so what is this number? This F value goes from 0 to 1. If it's 1, that means that we get 100% of efficiency. If it's 0, means that we don't have any efficiency. Usually, when we have solar thermal collectors, this F should be 0.6. It's good enough, but 0.6 is throughout the year. Okay, so in summer we should be close to 1. In winter, probably we will be close to 0.4, something like that. So the average throughout the year should be 0.6 to consider that system efficient, good enough. Okay. But the goal of calculating a solar thermal collector system, it's to calculate this F or this solar fraction, this F value throughout the year. And this is what the software that we're going to use does. The formula or the calculation that we have to understand is quite easy, and we know how to do it, or I explained last time how to do it. If this is a water pipe, and this is the inlet, and that's the outlet, and this is the solar radiation, what do we have? We have the amount of fluid. Through this pipe. This is the inlet temperature, and this is the outlet temperature. So what's the energy that we are absorbing? It's the amount of fluid times the specific heat of the fluid. This is the specific heat of water times outlet minus inlet temperature. Okay, so this is the energy that we are getting from the system. Usually, if we, and this is something that we have to understand, there are two things that we can control here. We can control the specific heat of water. This is constant, so we can't do anything about this. So we can control the amount of fluid, and we can control the difference between indoor and or inlet and outlet temperature. If we want to keep the energy constant, and if we increase the amount of fluid, then we will decrease the difference of temperature. But if we reduce the amount of fluid, we can increase the difference between indoor and inlet and outlet temperature. Okay, so these are the two strategies. Well, there's only one strategy. We can control the flow of water. If we want a gap, if we want to increase the gap of this temperature, if we want to really heat up water up to the temperature that we need, probably we need to reduce the flow, the water flow. But on the other hand, if we want to, using the same energy, if we want to keep this difference very low, then we need to increase the amount of fluid. So what do we want? Usually when we are working with solar collectors, what we need here is that the outlet temperature should be 140 Fahrenheit. What's the inlet temperature? It depends. Where does temperature come from? Imagine that we are in our house. We have a solar collector here, and this is the grid, the water grid. What's the temperature of this water grid? Is the temperature of the soil. If it's in winter, and here we have 0 Fahrenheit, probably the temperature of the soil buried like 3 feet down, it will be like 40 Fahrenheit. If we want this to be 140, so this is the inlet temperature and this is the outlet temperature. It's very difficult going from 40 to 140. Very, very difficult. So usually what we do, we have a water tank here. Okay, so this water tank, usually it's full of water and we are recirculating this through the water tank. So the temperature in the water tank, maybe it's not 40, it can be around 80. Okay, so this is something better. So that's why in these systems, we need tanks, we need water tanks. Otherwise, we need to use the water that comes from the grid. And the water that comes from the grid in winter, it can be extremely cold. Okay, but that's the idea. We want energy, and we have these three factors: the amount of fluid or the flow of water, and we can increase the amount of water that we are running with this pipe. We can't do anything with this, and then we have to consider the inlet or the difference between the inlet and the outlet temperature. So that's it. This is all we have to understand. And the only thing we can do, if we want a big gap between the inlet and the outlet, reduce the flow of water. If we want to reduce the gap between the inlet and the outlet temperature, increase the flow of water. And what's the technology? It's a flat plate solar collector. It's something that we can do on our own. Okay, so we need thermal insulation. We need a thermal insulation panel. We can buy this at the Home Depot. And then we need some pipes. We can buy these pipes in the Home Depot. And then we need a black absorber plate. Okay, we need something black so that it absorbs a lot of heat. If it's white, it reflects heat. If it's black, it absorbs heat. So this energy absorbed by this plate, it's a metallic plate, eventually is absorbed by the water. And then we need a transparent glass or plastic because we need to close this. Okay, so we need to allow this energy enter this cavity and then it doesn't go out because we have a glass here. So that's it. If we go to the Home Depot, we buy thermal insulating panels. We have a white plate made of aluminum, steel, or whatever, something metallic, and then some pipes, and then we weld those pipes to this, and finally we close this with a glass, and then we have a frame holding everything together. This is a flat plate solar collector. Okay, so it's this technology. It's not something that we can't understand. It's very easy. We need something black to absorb this solar radiation. We have this thermal insulation because we don't want this energy to go out, and so that's why we have thermal insulation here. That's it. Then there are other technologies, which is the concentrating collectors. This is slightly more complicated because with these collectors, we have a water pipe and we have different mirrors here, so that the solar radiation hits on the mirror, and then the reflected solar radiation goes to the water pipe. That means that we have to play with the geometry. If we have something like this F, if we have a parabolic mirror, well, the geometry says that every single sun or every single ray is reflected in this parabolic mirror, and they all the reflections meet on the same point, the focus on this parabolic shape or this parabolic mirror. So if we place this pipe in the right place, all the reflected solar radiation meets on that place, and then we maximize the amount of energy that this pipe is getting. Do we have this at home? We usually don't have these kind of devices at home. Okay, you can find devices like this to heat up water in residential buildings, but usually what we have are these kind of solar fields with these parabolic mirrors, and there is always a pipe. Well, this is the strategy. We have the parabolic mirror here, and there is a pipe placed so that all the reflections meet at that point. Okay, so that's it. This is very efficient, and we use this to generate extremely hot water. Okay. We have thousands of mirrors like this. Then we have a tower. Usually all these mirrors are, the reflection of all these mirrors are pointing at this, at the top of the tower. Here we generate a lot of energy, and then we evaporate water. We create water steam. So that's the, okay, so at large scale, we can have all these elements to produce electricity. We don't have this at home. Okay, so this concentration or solar technology, we don't use this at home. It's very efficient because we can track the sun, we can move the mirrors so that every time we have a, when the sun changes, we can always direct the reflection to the same point, at the same point, and then we generate a lot of, okay, so this is impressive because we can have I don't know, acres with this kind of solar collectors, and they all direct the reflected radiation to that point. Okay. There are different versions of that. Yeah, so that's another version. Instead of having this tower, we have this pipe running here, Okay, so all these mirrors are heating up the water that goes to this pipe. So we don't use this. Well, maybe you can find something at the domestic scale, but it's not usual. What we usually have is this, the most common solar collector is this flat plate solar collector. So there are three technologies. We have the flat plate solar collector. We have these concentrating collectors. We don't use it as a building at a building scale. And finally, we have the heat pipe, what do you call it? Or yeah, it's the heat pipe technology. Heat pipe solar collector. There you go. So what is this? It is a pipe, as you can see, it's made of glass. There is vacuum here, so we don't have air. So there is a way to extract all the air from this pipe here. And then there is a fluid. Okay, so there, this element here, it's not water, it's a fluid that changes from solid to liquid. So how does it work? So in the section, there are like 2 glass pipes together. Okay, so here we have the fluid. It's not water. And here we have the vacuum. Okay, so there is no air there. So if we look at the pipe this way, the fluid will be here. And this bottom part of the pipe, this is a mirror. Okay, so this works as a parabolic mirror, so that all the rays that come here, they are reflected to this point. So what happens at the beginning? This fluid is solid. If we have solar energy heating up this fluid, it turns into liquid. And when it turns into liquid, it goes up. And here we have a valve, like a thermometer. Okay, so this fluid that at the beginning it's a solid, it heats up, it becomes a liquid. And here we have a water flow. This is the water. This is the inlet. This is the outlet. And this fluid releases the heat to the water, so that from liquid it becomes a solid again, it goes down, and then we have the cycle. Okay, so basically we have something that it's solid at the beginning, we heat up this, it turns into a liquid, the liquid goes up, there's a water flow here, this liquid releases the heat in the water heats up, and then the liquid becomes solid again, and it goes down. So that's this. We cannot do that. If we go to the Home Depot, we won't find this kind of materials. And this fluid, it's something that we cannot buy anywhere. Okay. So this technology is more advanced. the panel is more efficient, and it's even more beautiful. Okay, so here you have a picture between a difference between the two technologies. So this is the flat plate solar collector, and this is transparent, and it's cool. Okay, so people like this kind of technology. This is like ugly, and as time goes by, this becomes even uglier. But that's fine. That's beautiful. So you can think of this even as the envelope or as a skylight, because it's kind of transparent. Okay, so people like this kind of technology. It's more efficient. It's more expensive upfront, but I mean, it's competitive. This technology is competitive. I told you that we have these kind of panels, these heat pipes in this building. Right there, the domestic hot water in this building is generated with this kind of heat pipe panels. Okay, but this is the technology. This is the heat pipe. Well, it can be flat, like an absorber plate. It can be this parabolic mirror that I told you. But the thing is that the fluid that we have here is different than the water. So here we have the water, the cold water, and then we have the hot water there, because it's taking the heat from the fluid that we have in this tiny cylinder here. So that's the technology. What is the hot water consumption? This is something that we have to do before doing anything else. We have to calculate the water consumption of our building. First, what is the temperature? Well, here we have the temperature, lavatory, hand washing, shaving. It's from up to 105 Fahrenheit. If we are taking a shower, 115 Fahrenheit, it's good. Residential, dishwashing and laundry, it's up to 140 Fahrenheit. And then, well, this is residential, and then there are other sanitizing or nursing units. Okay, so we can get up to 180 Fahrenheit. But for residential buildings, we need to heat up the water up to 140 Fahrenheit. Okay, that's very hot. If you are exposed at 140 Fahrenheit, you will get burned. Okay, so the 115 is the maximum temperature that the human body can bear. Okay, more than 150 would be, but we need 140, and this is like a magic number because we kill this guy, the Legionella pneumophila, or something like that. This is a bacteria, and when we have water below 140 Fahrenheit, this bacteria can appear, and this is poisonous, and people can get well, yeah, so it generates a lot of illnesses, this bacteria. So that's why we need to heat up water up to 140, because at that temperature this bug or bacteria or whatever dies. Okay, so we need to, even though we don't need that such a hot water, because with 140 we need to mix, but at the tank the temperature, the water temperature should be up to 140 Fahrenheit. Okay. So first, if we have a system, what is the outlet temperature? The outlet temperature should be 140 Fahrenheit. If it's not enough, we need an auxiliary system. Okay, but at some point in our hot water installation, we need to get up to this 140 Fahrenheit. And these are the typical household hot water demands. We're talking about daily. Okay. The first number is liters, and the first number is gallons, and the second number is liters. So we have 20 gallons for a bath, 20 gallons for a shower, 2 gallons for shaving, for face, hands, and washing, 4, teeth brushing, food preparation, automatic. Well, those are reference values. If you are 2 hours under the shower, probably you will waste more water, but these are average values, okay? And these are daily values. So you can have an idea of how much water we need in a single family house or even a building. If we have this building here, do we brush our teeth here? Hardly ever. Do we prepare food? Not that I know of. Do we have showers in this building? I haven't seen any. Do we have a clothes washer? No, I don't think so. Okay, so it depends. But if you go to the recreation center, there are a lot of showers there. Probably there are a lot of people not preparing food, but you have to dish, you have to wash the clothes for the athletes. Okay, so the hot water that we need in different buildings depends, especially if we have showers or we don't have showers, and if we have a clothes washer or we don't have it, or dishwasher in restaurants, probably we will need a lot of hot water, but it depends. Okay, so we are going to work with single family houses, and what's the amount of hot water that we need per day? This. Here we have another table, and this is the well, the average per day in food service, in restaurants, in apartment houses. Well, look at this. In apartment houses per unit, it depends on the number of apartments. Usually, the more apartments, the less water we use per apartment. Why? Because probably not all the apartments are occupied at the same time. Okay. So in an apartment building, if we have 20 or less apartments per day, we are using 42 gallons. If we have 200 or more, we are using 35 gallons. Okay, so something from 30 to 40 in apartment buildings, it's good. And then we have dormitories, nursing homes, office buildings. In office buildings, look at this. We have a gallon per person. Okay, so depending on how many, this is what I would do. Do we use a gallon per person in this building, in educational buildings? This is junior and senior high school per student, 1.8. Well, this is what we have, okay? So we have to make a decision, and the first decision is the amount of water, of gallons per day that we are using in our building. Then we need a tank, okay? So that's important. And there's a rule of thumb. What's the size of the tank? It's 1.5 or 2 gallons per square feet of collector area. Okay, this is the collector area. Usually these collectors are 6 feet by 3. Kind of, okay? So each collector is around, let's say 20 square feet. Can be from 15 to 20. Let's round up, 20 square feet. If we have 3 collectors, the collector area is 60 square feet. What's the size of the tank? It's 60 square feet times 2, 150 gallons. Okay, so that's a rule of thumb. It can be 1.5 to 2. Let's remember 2. So first we need to calculate the area of our collectors, and then we have to multiply this by 2, and this is the volume of the tank. So here you can see that in residential installations, we have 50, 60, 80, or 120 gallons. So 50 to 60, it's enough for 2 occupants, 120 for 4 to 6. Again, rules of thumb. If you go to your house and you look at your tank, I don't know, depending on how many people, it would be from 50 to 120 gallons. And for larger commercial buildings, we need a larger tank or different tanks. Sometimes it's cheaper having different tanks than having a huge tank like this. Anyway, these are the things that we need to know. So imagine that we are going to work with a residential building of 20 apartments. Okay, so let's do this. So we are working with a residential building, 20 apartments. Apartments. How many gallons per apartment? If we have 20 apartments, we can say 40, 42 gallons per day. Okay, so let's type 42 gallons times 20 apartments. So this is 84 gallons per day. Okay, so this is the amount of water that we need, 84 gallons per day. What we and we're going to do something like that, the most simple installation that we can have. Okay, so we have solar collectors, we have a tank, and then we have domestic hot water. We need a boiler, and this is the auxiliary system. If we don't have 140 Fahrenheit here, and it can happen because on a cloudy day, we won't have enough sun to heat up water up to 150, and we need an auxiliary boiler. This boiler, if it's electric, it's up to you, but is the best option, is the worst option. If you have a gas boiler to heat up water, it's a better option. If you want an electric boiler, make sure that you have PV panels to generate the electricity that you need to run the electric boiler. But we are not talking about that yet. Okay, so it's just solar collectors connected to a tank. We have another boiler, an auxiliary element connected to the tank, and we make sure that the temperature, the hot water temperature, can be up to 140 Fahrenheit. This is what we need. And to calculate, what do we have to calculate now? These are the data. Okay, so we have a residential building with 20 apartments. This is the data. This is all we have. And the first thing is calculate the hot water consumption per day. So it's 40 gallons per day. The second would be use F chart to calculate the area of collectors. And I told you that this technology is not quite expensive, but the more collectors we use, the more expensive the installation will be. So we have to, minimize the collectors that we need for the energy that we need, or the amount of water that we need to heat up. Okay, so it's not like how many collectors? 1,000. No, because it can generate a lot of issues. Okay, if we have if we have collectors and we have a tank here, in summer, the problem is that we can't do anything to help that. Probably in summer, we're going to generate more energy than we need. And we have, with this technology, I told you that there are problems in winter because we have freezing, but in summer, if the temperature that we get in this collector is above the boiling point, the system bursts. Okay, so we have to be careful in winter and we have to be careful in summer. If we place a lot of collectors and all of these collectors are exposed to the sun in summer and they are heating up water, at the end here, we don't have 140 Fahrenheit. We have thousands of Fahrenheit, and then the system bursts. We can prevent that from happening, having a huge amount of water. Okay, so that's why we need a tank, depending on the area of collectors. The more the area of collectors, the more water we need. Because if we have a very small tank with a lot of area of collectors, we can heat up the water above the boiling point. Okay, so we need a balance between the area of collectors and the volume of the tank. So first, we need to calculate the area of collectors, and then we have to calculate the volume of the tank. And then we have to check the solar fraction F. And usually this F has to be above 60. If we are above 60, we have done a good job. If it's below 60, we don't have the hot water we need. And but we have to be careful because at some point it will be, if it's more than 1, it means that we are getting dangerously to the boiling point. Okay, so we have to check that, and that's why we need to use the software, the ARCH. Okay, so this is to calculate solar thermal collectors. This is the only data is about the building. I'm talking about the residential building with 20 apartments. If it's a commercial building with, if it's a gym with 20 showers, then we have to go to that table, and then we have to find out how much water we need. Okay, but let's do this. We know that we need 84 gallons per day. So let's open ARCH. If it doesn't work, I have to go to my PC, local disk D. Here we have ARCH, and open this one. Okay, so there are like 3 different windows. We have the pool heating system, we have the flat plate collector, and we have the economic parameters. We are not going to work with the economic parameters yet. So first, well, let's go step by step. Here we have file to save. With this demo, you can't save a project. Okay, so that's if we want to spend $100 or $200 on this software, go ahead. But with the demo, we can't save the project. So we have to start the project and finalizing it right away, because we cannot save it and continue later. Then we have edit, nothing. Preferences. Okay, in preferences, we have economics on or off. I would use off so far. And here we have international and imperial units. So select preferences, economics off, English units. System. This is important. By default, we have the pool heating. That's another thing we can do with solar panels. We can heat up pools. Okay, if we have an indoor pool or we have spa or whatever, we can use the solar panels for that. but we are going to use the most, well, the first solution, which is domestic hot water, just domestic hot water. Okay, so select this one. And now we have active domestic hot water, and we have the flat plate collector. This is all we need. Okay, so in system, select the first one. In collectors, we can select the flat plate, the evacuated, this is the heat pipe, evacuated tube, or we can have a parabolic with tracking. I don't know, in buildings, I would use either this one or that one. Okay, so let's use the flat plate again. The evacuated tube will be better in terms of efficiency, but let's use the flat plate so far. In weather, we can select data location. If we had the full version, we could select the city. But in this version, we can select just the northeast, northwest, south, central, southeast, southwest, or upper Midwest. If we are in Keene, we are in northwest. Okay, so select northwest and northeast. Yeah, sure. So northeast, sorry. So weather, let me check northeast. Okay. And here we have run plot. Okay, before running the system, we need to change this. Okay, we can start here. Okay, so let's start with this window, the domestic hot water system. First, location, northeast. Then water volume to collector area. Yes, 2 gallons per square feet. This is the rule of thumb. Then fuel, because we are using the fuel, it's for the auxiliary source of energy. So in this, okay, so we have this boiler. It can be gas, it can be electric. As I told you, I would use gas. Okay, so I would use gas for this. Then the efficiency of fuel usage. Well, that depends on the specifications of this boiler. 70, it's too low. I think 80, it's better. Okay, but again, we have to look at the specifications of this boiler, and then we have to, what's the efficiency of the boiler? 80, 85, 79, whatever. So I think 80 is good. Daily hot water usage. So this is what we have calculated here. So the daily hot water usage is 84 gallons. So here we have to type 84. A water set temperature, 140. This is mandatory. Environmental temperature, what's this? That's the temperature where the tank is. If we have a tank outdoors, I don't recommend you do that. This temperature can be 0 Fahrenheit, and then the efficiency of the system will be affected for that. So please place the tank indoors. It doesn't have to be a heated space. Well, 68 Fahrenheit is almost comfort. I don't know, but make sure that the temperature around the tank is no lower than 60 Fahrenheit. Okay, if you place it on the basement, if you place it in the attic, well, try to control the temperature. It's not mandatory. You can place here, you can type here 20 Fahrenheit, but if the environmental temperature, the temperature around the tank, it's very low, the efficiency of the system will be affected. This is the UA of auxiliary storage tank. What does it mean? What does it mean, UA? If you remember, the heating load, it's U times A times inlet minus outlet temperature, or indoor minus outdoor temperature. Okay, so the UA is this value, the thermal transmittancy times the area of the tank. If we have a tank, usually a tank, it's like a cylinder. and it does have thermal insulation in the walls. Okay, so a tank, it's something metallic, but it does have thermal insulation in the wall. So again, this comes from the specifications. If we open a water heater, water or domestic hot water tanks, okay, this is a domestic hot water tank. And if we open the specifications, this is 38 gallons. It can be combined with natural gas, with a water heater, natural gas. And do we have information about the UA? No, we don't. Gas. First, we do have any information about the insulation. We don't. Anyway, this is something that we need to find out. Okay, so if we are buying a water heater or water tank, make sure that you need this information. It should be placed somewhere. Okay. If you don't find it, talk to the provider because we need information about this. Can we use this value by default? Yeah, we can. Okay, so it's a cylinder. We have usually we have how many inches of thermal insulation? 2 inches maximum. So we don't have 10 inches of thermal insulation for this kind of tanks. And what's the area? It depends on the volume of the tank. Anyway, by default, we can leave this value, but we have to find this in the specifications of the water tank. Then the pipe heat loss. We can select no or yes. If we are optimistic, we can say no. What does it mean? The more pipes we have outdoors, the more heat we can lose. So that comes with the design. If we are designing this system, and this is the roof, this is the house or the building roof, and the pipes immediately goes indoors, we can assume that we don't have any heat losses. Okay. If we have a lot of pipes exposed outdoors, then there will be a lot of heat loss. So this is our decision. If we type no, that means that we are optimistic and we have the panel placed on the roof, and immediately we go inside the building. And the environment inside the building, it's around 60 Fahrenheit. So that means that we are not losing heat. If we select yes, then we need information for the inlet and the outlet pipe. And this is the UA. So again, we need to know the U value, and then we need to know the area of the pipe. That makes the life more complicated. Do we have insulation for pipes? We do. If you have look at your the boiler or something, usually the pipes are wrapped with this kind of element, okay, with this with thermal insulation like this. So again, this element will provide you with the UA value. The U value, the thickness of the thermal insulation, and the area is the perimeter of the. It depends on the size of that circle. Okay, so again, if you look at this. At some point, okay, we have the R value of this insulation, it's 2.9. And if the diameter of the pipe is 2 inches, so what's the area of a 2-inch diameter circle? We have to calculate this area. We have the R value. the inverse of the R value is the U value. So if you have the area of the pipe and the U value, we can get this point. We can get this again. Talk to the or do this once in your life. Okay, so I'm using a 1/2 inch thick insulation. 1 inch. I don't like it. Anyway, you can type no. That means that you don't have pipes exposed outdoors. If you type yes, then we need this value. So let's leave 5. Okay. And finally, we have a collector store heat exchanger. Okay, that's interesting. A collector store heat exchanger. What does it mean? Okay, as you can see here in this schematic view, we have pipes. The water goes up this way. The sun heats up this water, and then it returns to the tank. Okay, and then as you can see that this red color turns into blue. Why? Because the water here, if we heat up water here up to 140 Fahrenheit within the solar collector, then we have to release this water to the water tank. Okay, so here we have the white space is water, and here we will have thermal insulation. This gray wall can be the thermal insulation of the tank. So this is the tank, and the tank is full of water. And then there's a pipe here, and the water here is at 140 Fahrenheit. Okay, so imagine that we go through the tank this way. This water is at 60 Fahrenheit. This water is at 140. So part of this heat is released to the water tank. If we have just one pipe, the amount of heat that we transfer is not that much. So that's why we it's not just a pipe. We bend the pipe many times, and we create like a coil, and then we transfer more energy. Okay, so that's why we have this. This is what we call a heat exchanger. Okay, we have water at one temperature here, and our goal is that all this heat is transferred to this water. So at the end, this water will be at 100 Fahrenheit, let's say. And then we need another boiler. This is the auxiliary boiler. And eventually the water will be at 140. Okay, so that's the system. And those are heat exchangers. We can have a system in which we don't have a heat exchanger. We can have a tank, the solar collector, and the solar collector is just like this. So the water that is here in the tank goes up through the solar collector, and then it returns to the tank at a different temperature, and we don't have this heat exchanger. This is more efficient because, yeah, we always lose some heat in this heat exchanger, not all the temperature, not all the heat here is transferred to the tank. But on the other hand, the water that we drink, because this is the water that we have in our shower, okay, so this is the water that we end up using, we end up drinking, or we end up in contact with. It's the same water that comes through the solar collector. In theory, it's not dangerous, but if we are below the freezing point here, we need the anti-freezer. The same thing we have in our car. If we have this fluid, if this is not water, then we can be exposed to this fluid, and then we need the heat exchanger. Okay. So if you are sure that the water that goes through the solar collector doesn't need this, you don't need the heat exchanger. But if you need this, and in this country you need this, you can drink, or you can be exposed to this water with this fluid here. So that's why we need a heat exchanger. In summary, I recommend you, because even in warm countries, there is a moment in which you can be below the freezing point. And if you are below the freezing point, the system bursts. Because if you have ice within these pipes, the ice expands and then the system bursts. So use always the anti-freezing and use always the heat exchanger. So here I would recommend you type yes. Tank side flow rate per area. Yes, so that's the amount of fluid. And this is the heat exchanger effectiveness. This heat exchanger effectiveness, 0.5, it's 50%. I think it's quite low. So let's type 0.8. But as you can see, those are things that are the losses of the system. The heat exchanger effectiveness, if we don't have insulation in our in the pipes, if the tank is outdoors and the environment temperature is not close to comfort temperature. So all those are things that affect the system. Okay. Something else, the most important thing, location, the water volume to collector area. This should be always around 2. Whether what kind of fuel or what kind of auxiliary system we have, gas, in my opinion, would be the best choice, unless you have PV panels and you have an electric system, but let's use gas so far. The efficiency of fuel usage, it should be above 80. If it's below 80, this boiler, it's not good enough. The hot water usage, we have had to calculate the hot water usage with the table. The water temperature is always 180. The environmental temperature, the tank should be always indoors. If it's indoors in the living area, in the bathroom or in the kitchen, you can type here 70 because it's a comfort temperature. If you are not, well, it depends. If it's outdoors, you have to take the outdoor temperature, not recommendable. If you're in the basement, is the basement heated up? If you have a heating system in the basement, you don't, it depends. And then the thermal insulation of the tank, the thermal insulation of the pipes, and finally the heat exchanger effectiveness. I would recommend you use a heat exchanger always. But if you don't, it's acceptable. But remember that if you don't have a heat exchanger, you can have the anti-freezing fluid in the system. Okay, so this is the system. What about here? Now, the number of collectors. Okay, it's like a try and error. You can't calculate the number of collectors. Well, if you have experience, you know what it takes. Oh, I have 80 gallons per day. 3 collectors is enough. Let's try this. If we try 2 collectors, the collector panel area, I told you that it's around 20 square feet. In this case, it's 20.8. Okay, 20.8. And these are values that depend on the collector. Okay, so we have to go to the specifications of this collector, and these FR, UL, alpha, tau, those are big letters that depend on the efficiency. This is about the efficiency of the collectors. So this is somewhere between 0.7, 0.74. It's around 70% of efficiency. Okay. It can be better. 80 would be better than 70, but that depends on the collector. The slope, this is something that you can control. If you have 45 degrees or you have 30, so let's imagine that it's 30. The collector azimuth, it has to be 0. It has to be south oriented. If it's not, okay, so make sure that you have the orientation of the collectors. It's always 0. It's always south. And the numbers of glass covers, you can select 1, 2, 3, 4. 2, it's common. It's like double glazing, triple glazing. You remember that we have glass because we have selected the flat in options or in collectors. We have selected the flat collector. And remember that, okay, so here in this case, this is a double glazing. So the number of glass covers, it's 2 in this case. It can be 3, 4, or just 1. The more the better, the more expensive. I think 2, it's good enough. So 2. Collector flow rate. Okay, so this is tank side flow rate area and collector flow rate area. Well, these 2 values, in this case, they are the same. So we assume that the flow rate in this circuit is the same as the flow rate in the collector. Okay, so the flow rate that we have here is the same flow rate that we have in the collector. It makes sense, but it might be different. Okay, so in this case, leave this number. The specific heat. This is the specific heat of water. So if we add some of these anti-freezer, this might change, but it doesn't change. Maybe it's 0.79 or 0.81. You can leave 0.8, which is the specific fluid, the specific heat of the water. And that's it. Okay. So here, the most important thing is the collector, the number of collectors. I don't know if it's going to be good or bad. So let's try with 2 and run, calculate. Okay. So if we calculate here, we have all the information that we need. The first thing is the F value. The F value ranges from 0.05 up to 0.39. Do you think it's good or it's bad? Would you be happy with this? Yes? Why? I don't know. You're happy because we are done. Okay, I'm tired of this. No, I'm not happy at all, because this should be close to 1. Okay, so it has to be above the requirements. It has to be above 60 or 0.6. Okay, so that means that with this amount of collectors, in summer, we can get only 40% of the domestic hot water. So I don't like it. Let's move it to 5. Let's run again. Okay, so if we have 5 collectors, now, okay, it's not bad. So the yearly value, it's a 0.5. You see that it's, I want to, this goal should, or this number should be 60. So 5 collectors is not, let's try 6 and calculate again. Okay, so now it's 0.59. And we have to look at 2 things. We have to look at the average value of the year. If it's 0.6, this is for 0.59, so it's 0.6. And this, the maximum value, it's 0.9. So that means if we are above 1, we're in danger because in summer it will be too hot. And we have a risk that in summer the system can be damaged, okay? But I think we still have, because this is 0.9, so I will go with 7 collectors, calculate, and even with 8 collectors. Calculate, okay. So I think now we're at 0.7. 0.7 is quite good throughout the year. In January, we have only 0.3. So in January, only 30% of the domestic hot water can be generated with collectors. And here we are, the problem is that this system doesn't have, when it gets to 1, it doesn't go farther. Okay, so we don't know if it's 1.1. If it's 1.1, doesn't matter. But if it's 5, we're in danger that the system can burst in summer. So no, I would between 7 and 8. Okay, with 7 we don't get to 1, so I think 8 would be enough. Okay, so 8 will work well. And then here we have the solar, domestic hot water, and the auxiliary. This is the amount of energy that we have from the sun. And this is the amount of domestic hot water that we are generating. Okay, so out of 73 times 10 to the power of 6 BTUs, we are generating only 27. Okay, so that's the efficiency. We are losing energy from 73 to 27. This is not 80%. Because we have 80% of efficiency, but then we have losses through the tank, we have losses through the pipes, and we have losses through a lot of things. Okay, so we are losing energy. So if those numbers are too close, that the closer the better. Okay, this is 73, this is 27. Okay, it could be better. And this is the amount of auxiliary energy that we need. Okay, so this is the energy that we are generating with our system. And this is the amount of auxiliary energy that we need. We don't need any energy in auxiliary energy in July and August. We need very few energy in September or June, but in December and January, probably we need, well, it makes sense, okay? But try different number of collectors, and the goal is that the year average should be above 0.6, and make sure that we are not very far from 1. If you type, for example, 20, and we calculate, we say, oh, 1, it's much better, because most of the time we have yeah, so now the average is 0.93. Okay, so even in February, yeah, but the problem is that here we don't know if this 1 is close to 1 or it's dangerous. Okay, so that's why I wouldn't go for 20. I think 8 will be better. What about 10? If I want to do this, I would increase the water volume per collector area. So let's make it 4. And I'm keeping 10 collectors. And if I calculate, well, I don't know. That's becoming dangerous. Okay, so when we have a lot of 1 values here, that's great because the system can be damaged. Okay, so around 8 collectors, I think would be and if this is 2, yeah, 8 collectors would be. And now what's the size of the water tank? The size of the water tank is 8 collectors times 20 square feet per collector times 2 gallons per square feet. So this is 8, 16 por 20. 320 gallons. We have seen that more than 120 gallons, well, probably will need more than 1 tank. Or if we find that, again, this is about the price. Is it cheaper having a 320 gallon tank, or is it cheaper having 3 tanks of 120 each? Depends. That would be the volume of the tank. Okay, and the area of collectors, we need 8 collectors times 20 square feet.